What is work? Now, please, I want us to note that work is done when a force is applied to an object. All right? So, first thing we must note is that work is done when a force is applied to an object or a body. All right? So, the amount of work done is the product of the force and the distance moved in the direction of the force. So I'm saying that the amount of work done is the product of the force and the distance moved in the direction of the force. So that is the definition for work done. Now, from this definition, I can derive a formula for it. So I can say that work done is equal to what? The force times a distance. So here is a formula for work. Now, from this formula, I can derive the unit for work. Now, force is in Newton, okay? Then for distance is in meters. So therefore, I can say that the unit for work is Newton meters. So it's Newton meters. Okay, now I want us to also note that some units have a special name. Newton meter can be called joule. It can be called joule. And please, we must note at this point that 1 joule is equal to 1 Newton meters. Very important to note that 1 joule is equal to 1 Newton meters. So therefore, work can also be measured in what? In joules. So you can measure in Newton meters or in joules. Now, work and moment has the same formula. Work and moment has the same formula. All right. If you remember, moment is equal to what? Force times the what? The perpendicular distance. So moment and work has the same formula, but in this case, the distance is in a different direction. For moment is what? A perpendicular what? Distance. For work, the distance is in the same direction as the force. Okay. Now, I want us to also note that 1000 joules is equal to 1 kilojoules. Very important. When solving energy, sometimes we have to use a prefix to reduce a large number. So please note that 1000 joules is equal to 1 kilojoules, and also 1 million joules. 1 million joules is equal to 1 megajoules. 1 megajoules. Please, you have to note this before we start looking at questions. Let's look at a question right here. We are asked to calculate the work done when a force of 70 Newton pushes an object a distance of 500 meters in the same direction as the force. As always, the first thing I do is to write out my given data. I'm given the force of 70 Newtons I'm given a distance of 500 meters. My distance is 500 meters. We are asked to find the work done, W. Now, the first thing we do here is to extract or bring back the formula, which is work done is equal to the force times distance. What next? I log in my data. For the force is 70, so I have 70 right here, times my distance is 500. So when I multiply this, I get 35,000 joules. 35,000 joules. Joules, or it can be 35,000 Newton meters. Okay? Newton meters. Now, I can convert this to kilojoules by dividing by 1,000. When I divide this by 1,000, I get 35 kilojoules. 35 kilojoules. Or I can say 35 kilo Newton meters. So here is our final answer. Now, area under our first distance graph. Now, sometimes we are given a question and we are asked to find the work done in a first distance graph. Now, the work done in a first distance graph is the area under the graph. Look at this. The work done in a first distance graph is the area under the graph. Now, what I'm saying here is that the work done for a first distance graph is equal to the area of that shape. I can say, in other words, the work done in a first distance graph is equal to the area of the shape, or the area of what? Of the graph of that shape. Now, a first distance graph is also called a work diagram. A first distance graph is also called a work diagram. Okay, so this is the concept about area under a first distance graph. It is the area under that graph, and very soon you will see that it is very, very simple, because area of shapes are what we all know in our maths and in our lower level physics. Now, the first graph we draw here is called a constant force. Now, most times when we are to draw a constant force graph, most times you may not have to sketch, all right? But some other times you might have to sketch to get the accurate value, all right? Now, I will show us how a graph with a constant force looks like, and I will show us how a graph with a spring extension looks like. Now, for a constant force, the graph looks like this. Look at this, guys. For a constant force, the graph looks like this. As you can see, all right. All right, cool. So guys, what we are seeing here is a constant force graph. It looks like this. As you can see, it's a constant. Right here is our force, okay? While right here is our distance. Here is our distance, D. Okay, now the area under this graph is the work done. So the area is the work done. So as you can see, here is a rectangle, or it can be a square. So I can say that the work done in this case is the work done is equal to what? The area of what? The area of the square, which is the what? The area of the square. The area of the square. Of the square. Now, the area of a square is what? Is length times width. So therefore, I can say that the work done for this graph is the force, which is F, times the distance. So right here is the formula we can use to solve a force distance graph that has a constant force. So this is the equation to solve a force distance graph with a constant force. Now the graph for a spring extension looks like this. Look at your screen, please. I'm drawing the graph for a spring extension. Right. So guys, what we are seeing here is the graph for a spring extension. Right here is our force, F, and right here is our extension. I call it extension because it's a spring. It's our extension. All right. Now, the work done in this graph is the area under the graph. So right here is our work done, and please note that right here is the force, which is the height in this case, is the force. All right, so the area or the work done for this graph is what? Is equal to the area of the triangle. As you can see, here is a triangle, so the work done in this case is work done equal to the area of a triangle of the triangle. So I can say area of triangle is half times what? Base times height. So I can say half times the height, which is F, times the what? The base, which is our extension, E. So right here is the formula we can use to solve for work done involving a spring. For a constant force, please note that the graph is in this format, while for spring, the graph is in this format. I will show us examples of how we can apply these concepts to solve questions. So for this question, it says, step 1, I will draw my graph. I draw my graph. Okay. Here is the force, and here is my distance. And please note that it says at first it was what? Supplying 2000 Newton of force. So here's my 2000. Here's my 2000, guys. Look at this, 2000 Newton. Now from this point it moves what? It moves 7 meters. So it moves 7 meters. All right. Here's my 7 meters. It says the force is changed to what? 800 newtons. So it changed to what? 800 newton. This is my 800. It changed. That means that at 800 it moves a further of what? 20 meters. That is to the right. That is what? 27 meters. When you subtract this, you get 20. Okay, so it moves what? A further 20 meters, which is what? 27. Now I can now solve or determine the work done from this graph. So you see that drawing the force distance graph will help us a lot in being able to solve the work done by this method. Now to solve this question, as you can see right here, I have two rectangles right here. So I will split into two. Here's my rectangle 1. This is my what? Rectangle 2. So to get the work done by this method, I will find the area under this graph and the area under this graph, and I will add up. So I can say therefore that the work done is equal to what? The area of the first rectangle, let me call it A, area of the first rectangle, rectangle 1, plus the area of my rectangle 2, of rectangle 2. Now my first area is right here, is length times the width, is what? 2000 times what? 7. So for my first area is 2000 times 7 plus the area of my rectangle 2, which is what? 800 times the distance between 7 and 27, which is 20. Is 20. When you subtract this from this, is 20. So it's 20. So therefore I can now get my values. This gives us 14,000 plus this gives us 16,000 so we can add this up and we get what? We get 30,000 joules. Now I can reduce this further to kilojoules, so I will divide by 1,000, becomes what? 30 kilojoules. So here is our final answer to this question. Good. So I was saying for this question, as you can see, it's a spring. So I will draw my force distance graph. Okay. And I say that here is my force and here is our extension. Now as you can see is 70 millimeters extension. So from my origin, all right, so here is 70 millimeters, and the force is at 20 Newton. All right. Now, question, we are asked to determine the work done in extending the spring from 0 to 40. And here is my 0. And let's call this point my 40. So, to get the corresponding force at 40 millimeters, we have to use our graph. As you can see right here, to get the corresponding force at 40 millimeters, we have to draw our graph. So I have to come to the graph paper. Right here is my force in Newton. Right here is my extension in millimeters. Then step 2, I have to choose a scale. Now here's my 0.0, so I can use a scale of 2 cm to 10 units. All right, 2 cm means that 0, 1, 2, here's my 10, here's my 20, 1, 2, here's my 30, 1, 2, here's my 40, 1, 2, here's my 50, 1, 2, here's my 60, here's my 60, 1, 2, here's my 70. Okay, now for my force is at 20 newtons, so I will also use the same scale. I will use 2 cm to 10 units, 2 cm to 10 units on the y-axis. So 0, 1, 2 is 10, 1, 2 is 20, and 1, 2 is 30. I can stop right there because the highest value for my force is 20. Now, the next step is to draw the extension. So it's from 70 to 20. All right, can make it thicker. Good. And it is a spring from 0 to the spring. So that is my force distance graph. Now, question 1, we were asked to determine the work done from 0 to 40. So therefore, I can determine the work done from 0 to 40. So from 0 to 40, so from 40 to my line here, I have to determine the value of the force. Let me use a buccal line right there. A buccal line. Then from these points to my force axis. So guys, to my force axis. Now, from this graph, I'm seeing right here, the value or the corresponding value for my force as it relates to the 40 millimeters is 12. So I can say that F is what? Is 12. Here is what? 12. My F here is 12. It's 12 as gotten from the graph. Now, question A. We asked to find the work done from 0 to 40 millimeters. Now, from 0 to 40 millimeters is a triangle. As you can see right here, it's a triangle. So I can say it's equal to the area of the triangle. The area of the triangle. And that gives us half times the force, which is the height, which is 12, times the distance, which is what? 40 millimeters. Now, we can convert 40 millimeters to meters, and that gives us 0.04. So therefore, we can use our calculators to get the final answer. So 12 times 0.04 divided by 2, that gives us 0.24 joules. 0.24 joules. So that is the answer, or that is the work done from 0 to 40 millimeters. The work done from 40 to 70 can be done using what? Finding the area of the bigger triangle. I can find the area of the big triangle minus area of the smaller triangle, minus area of a smaller triangle. All right. Now, for the big triangle, which is from 0 to 70, it is what? Half times the height, which is 20, times the extension, which is what? 70 millimeters. We convert to meters, it becomes 0.07 meters. Right? Minus the area of the smaller triangle, which is 0.24. Which is 0.24. Okay. So what next? Half times 20 times 0.07 will give us 0.7 is 0.7 minus 0.24. So 0.7 minus 0.24 will give us 0.46 joules. 6 joules. So here is our final answer for the work done from 40 millimeters to 70 millimeters. Here is the final answer. Now, we can also solve this question using a different approach. We can also divide the shape into two, okay? And we can find the area of the triangle here and the area of the what? The rectangle. Then we add up and we get the same answer.